Hello, my name is Pedro Ribeiro and I'm a Physics Engineering Master student. In this video, I'm going to introduce you to my master thesis project, Tactile Sensing for Robots, Wearable Devices and Human-Computer Interfaces, supervised by Professor Susana Freitas of INESC and Professor Alexandre Bernardino of the Institute for Systems and Robotics. Human beings are the most dexterous of vertebrates, in part due to our remarkable sense of touch that is constituted by thousands of tactile receptors, enabling us to gather information about the physical properties of objects that surround us, like surface roughness and rigidity, that can't be perceived by vision alone. The implementation of human-like tactile sensors can open new frontiers for robotics projects that focus on human-machine cooperation, like the Robonaut project, with the goal of developing a robot capable of assisting side-by-side astronauts during space missions, or projects that aim to replicate human behavior, like the ICUP project, with the purpose of better understanding the human cognitive development by simulating a human child as perfectly as possible. But how is tactile sensing implemented on robots? Tactile sensing has two components: the intrinsic sensing, composed of sensors to detect the applied forces and angles of robotic joints, and extrinsic sensing, with the purpose of detecting the characteristics of the machine's surroundings. Although intrinsic tactile sensing is enough for industrial robots that operate on isolated environments and require task efficiency over variety, on humanoid robots, task variety and adaptation to perform new tasks is desired. The goal of my project is to develop a tactile sensor able to detect contact and small applied forces by mimicking cilia. In nature, the mechanosensing ciliary structure, that is, movement-detecting cilia, consists in a passive organelle called cilium with the form of an elongated protuberance anchored to an active organelle called dendrite that generates electrical pulses when the cilium is activated. This structure is found in most insects, granting them the ability to feel subtle movements or small flows. To imitate this structure, we'll be needing an array of pillars patterned and anchored to a sensor that can detect the pillar's movement and displacement. The implementation of such a setup can be made by patterning a flexible material with permanent magnetization over a thin film sensor detecting the magnetic field incident over it. The chosen setup for my project was to pattern iron nanowires that are long iron cylinders with nanometric diameters embedded in PDMS nanorods, a quasi-perfectly elastic material, in order to obtain flexible nanopillars with permanent magnetization. These pillars are then placed over a spin valve sensor, a magnetoresistive sensor that suffers a change in resistivity when a magnetic field is applied, by varying the magnetization of a ferromagnetic layer susceptible to be magnetized by the applied field, called free layer, relative to a layer with fixed magnetization, called pinned layer, intercalated by a non-magnetic layer. These magnetic sensors have high sensitivities, low power consumption, and can be made to have linear responses. Now I'm going to explain the ciliary sensor working mechanism, and although PDMS is transparent, to better observe the pillars, I'll make them golden. So, if the pillar's magnetization direction is vertical, then when a force is applied, the pillars bend and the direction and magnitude of the average magnetic field over the sensor changes, inducing a change in resistivity. Thanks to the high sensitivity of the spin valve, even a very small variation in pillar deflection induced by a small applied force leads to a resistivity variation high enough to be detected. Similar setups have been developed at KAUST, capable of detecting water flows with resolutions of 15 micrometers per second using giant magnetoimpedance sensors that have lower sensitivities than magnetoresistive sensors. In another experiment with the same setup, a ciliary sensor was able to detect forces with a resolution of 65 micronewtons, better than any other tactile sensor. In conclusion, by taking a cue from nature and imitating the ciliary structure, we're expecting to fabricate a sensor capable of detecting very small contact forces with low power consumption by using a spin valve, a more sensitive magnetic field sensor than the one used for the structure that yielded the best results obtained until now, hopefully contributing to make future robots sense like humans and feel more human-like. If you have any questions, or would like to know more about my project, please feel free to contact me through the email that can be found in the video description below and in the following credits. Thanks for watching.